Page 5 and 6 of discrete random variables. Number 5, continuation from last class. When rifle shooter Hui fires a shot, he hits the target 80% of the time. If he fires 4 shots at the target, determine the probability that he has 2 hits and 2 misses in any order, and that he has at least 2 hits. Let's expand this like it's a binomial expansion. So since it's a 4-shot experiment, it would be a 4th order Pascal's triangle. So 1, 4, 6, 4, 1. And then the probabilities used are going to be success 80%, failure 20%. So we'll have 0.8 to the 4th, 0.8 to the 3rd, 0.8 to the 2nd, 0.8 to the 1st, and 0.8 to the 0. And then in the reverse order, we would have 0.2 to the 4th, 0.2 to the 3rd, 0.2 to the 2nd, 0.2 to the 1st. Okay, so this is the binomial expansion. So these are all the possibilities, and there's one way to get 4 successes, there's 4 ways to get 3 successes, there's 6 ways to get 2 successes, there's 4 ways to get 1 success, and there's 1 way to get 0 successes. So what is the probability that you would get 2 hits and 2 misses in any order? 2 hits and 2 misses would be this middle term. So the answer would be exactly that. It would be 6 times 0.8 squared times 0.2 squared. What about the probability that you get at least 2 hits? At least 2 hits would be, it would be 2 successes, or 3 successes, or 4 successes. So it would be all these 4 added together. So it would be 0.8 to the 4th plus 4 times 0.8 to the 3rd times 0.2 to the 1st plus 6 times 0.8 squared, 0.2 squared. Okay? Binomial probability distribution function. Probability of x equals r. This can be written as a mathematical formula, right? And so basically it's like one of these terms here. We could write it as if it was one of these terms. So let's write it. We're going to put, we can write the coefficient as n chooses r. It would be the success probability to the rth power, and the failure probability 1 minus p to the n minus rth power. So it's pretty much following the pattern we see here above. Here it specifies that yes, p is the probability of success, n independent trials, r successes, and n minus r failures. This notation here, big X, tilde, capital B, n, comma p, is read as the random variable big X is distributed as a binomial experiment with parameters n and p. Here is a procedure to figure out binomial PDFs using the TI-84. So I'm going to show you how to use the calculator to figure out A and B for number 5. Remember that A was equal to 6 times 0.8 squared times 0.2 squared. If we do that on the calculator, we find that it's 0.1536. 0.1536. And if we want to do it with the binomial PDF function, what we do is we do second vars, which is actually distribution. We go to the second page and we choose binomial PDF. We choose binomial PDF because we only want to know the probability that we get a certain number of successes and not a range of successes. So we put 4 trials. Probability of success is 0.8, right? We want 2 successes Those are the only pieces of information we need. It figures everything out. It figures out the coefficient, multiplies it times 0.8 to the squared, the times 0.2, and it looks for the exponent of 2. So the answer, you see, it comes out exactly that with just those 3 parameters. Now let's see about B here. First, we're going to add up this probability here. I have it typed out already because it took quite a long time. And I'm going to have it calculate that the probability that he gets at least 2 hit is quite high. It's 0.9728. 9728. And then how can we figure that out with the calculator? Well, like I said, the calculator cannot figure out at least 2 hits, but it always figures out the 0 to something. So it can't figure out x is greater than or equal to 2. What it can figure out is x is less than or equal to 1, which is the opposite of that, and then you could like take the result and subtract it from 1. So let's do that. We're going to do second distribution binary CDF, binomial CDF, and we're going to put 4 trials, 0.8 success percentage chance. The x value I'm going to put 1 because we want to look for 0 or 1, and this will give us this very small number here, 0.0272. Now we're going to subtract it from 1 to find out what the complement would be. So the probability that you would get 2 or more, and what do you know? It's the same thing. Okay? So you can use these calculator functions, especially if you have a really big one. You might want to do it with the calculator. So, okay. Number 1. For which of these probability experiments does the binomial distribution apply? Justify your sentence. Justify your answers using a full sentence. So for the first one, a coin is thrown 100 times. The variable is the number of heads. Yeah, that sounds like exactly what we've been doing up until now. So yes, this is a binomial distribution experiment. N equals 100, and x is equal to number of heads. So what about the second one? 100 coins are each thrown once. The variable is the number of heads. This is actually the exact same as the first one. So yes, same as the first. Last one. A box contains 5 blue and 3 red marbles. I draw out 5 marbles, replacing the marble each time. The variable is the number of red marbles drawn. So yes, this is a binomial distribution experiment. N equals 5. P is equal to, the success would be red marble, so it would be 3 out of 8. X is equal to number of red marbles drawn. So these were all binomial distribution experiments. Which one of these could you change into a not binomial distribution experiment? Well, what about this last one? It has a box with marbles, and every time you drew out the marbles, you replace the marbles. You could make this into a non-binomial distribution experiment by not replacing the marbles. So let's say you draw out 5 marbles. Every time you draw a marble, you keep it out. If you did that, every time you drew out a marble, the probability would change, right? So in that case, it wouldn't be a binomial distribution experiment because the probability of success is not going to be 1 constant p. What about B? How could you change B so that was not a binomial distribution experiment? Well, you have 100 coins. Let's say that some of the coins are weighted so that you have more chance of getting heads or tails on that particular coin. So if you have some of the coins that are different probabilities than others, instead of just being 1/2, then that would also not be a binomial distribution experiment. Okay? Alright, let's move on to number 3. In a multiple choice test, there are 10 questions. Each question has 5 choices, one of which is correct. If 70% is the pass mark, and Raj, who knows absolutely nothing about the subject, guesses each answer at random, determine the probability that he will pass. Now this is very similar to what we did in our investigation. So let me, information we can get out of the problem here. In a multiple choice test there are 10 questions, so that would be n trials, or that would be 10 trials. Each question has 5 choices, so the chance that you would get a question correct guessing would be 1 out of 5, right? And then finally, if 70% is the pass mark, Raj, who knows absolutely nothing, guessing at random, what's the probability that he's going to pass? So that's, what is the probability that big X is going to be greater than or equal to 7 questions correct, right? Okay, so we can do this with the calculator, but remember, the calculator cannot calculate probability of X is greater than or equal to 7. What the calculator can calculate is the probability that X is less than or equal to 3, or less than or equal to 6, which is kind of the complement of X is greater than or equal to 7. It's the exact opposite. If you subtract it from 1, then that is what you get. So let's do that. We're going to use 3 numbers in the calculator. We're going to use Binomial Cdf function, and we're going to put in n equals 10, p is equal to 0.2, which is 1/5, and we're going to put big X is equal to 6, because we're looking for big X from 0 to 6. Okay, so let's do that. We're going to turn it on. We're going to go to second distribution. We're going to go down to the second page where it has Binomial Cdf, and then we're going to say there are 10 trials, and p is 0.2, and the X value is going to be 6. So the probability of getting less than 6, or 6 or less correct is huge. It's 0.99. Oh my gosh, it's really big. And so let's figure out the probability that he's going to pass. We're going to subtract this from 1. So we're going to do 1 minus, and then we're going to subtract this big probability. We're going to get something very small. In fact, we're going to get 0.000864. So we'll put here 0.000864 is the probability that X is greater than or equal to 7. Make sure that when you write an answer in scientific notation on your test, you never copy this as is. It makes it look like you don't know what you're doing. Write it instead as real scientific notation. So you're going to write 8.64 times 10 to the negative 4. Don't write e to the negative 4. Okay? Number 5. Records show that 6% of the items assembled on a production line are faulty. A random sample of 12 items is selected with replacement. Find the probability that none will be faulty, at least 2 will be faulty, at most 1 will be faulty, less than 4 will be faulty. So what we're going to do here is I'm just going to give you the parameters you're going to use on the calculator, and then we'll do a couple of these. Okay, so basically for all these, we want to say that n is equal to 12, right? Because a random sample of 12 items are selected with replacement, and find the probability that, okay, and so this will be 6% of the items are faulty, so the probability of success in quote-unquote success, because, finding a faulty item is not really success, but in this case it is kind of success. Okay, probability is 0.06, and then for each one we're going to have a different value of X. Okay, so here we've got those. Okay, probability that none are going to be faulty. So the probability that X is equal to 0, we are going to use X equals 0 on the calculator. Okay, and we're going to use PDF, not CDF. Okay, and let's see, for at least 2 will be faulty. That's the probability that X is greater than or equal to 2. So in this case, the calculator is actually going to calculate the probability. It's going to be 1 minus the probability that X is less than or equal to 1, And so we're going to use x equals 1, and we're going to use binary CDF. Okay? All right. And then let's write these down. Let's see. We're going to have probability that at most 1 will be faulty. So that's the probability that x is less than or equal to 1. And so we're going to use CDF, and we're going to use x equals 1. And then the last one, probability that x is less than 4. But the calculator doesn't do x is less than 4. It does less than or equal to something. So we're going to have to put less than or equal to 3. Okay, and we're going to use CDF because it's less than. Okay, and we're going to use x equals to 3. Okay, and so now let's plug these into the calculator and see what each one turns out to be. Okay, so first one, probability that none will be faulty. So we'll put second distribution, go to the second page, we'll go to binary PDF, right? And then we're going to put n equals 12, trials, p is 0.06, and x value is going to be 0. And it'll give us 0.476. So that's the first one. 0.476. Okay, and then the next one is at least 2 will be faulty. Now we're going to use CDF instead of PDF. So we'll do second distribution, go to the second page, binomial CDF. We're going to put 12.06, just as before, except this time we're going to put 1, right? And after we get this answer, we are going to subtract from 1, this answer, to get the real answer, because what we really found is the opposite of x is greater than or equal to 2. What we found is x is greater than or equal to 1. So it would be 1 minus this number, which is 0.160. 0.160. And actually, we're looking for the probability of x is less than or equal to 1 also. Here we found the probability is less than or equal to 1 is 0.840, right? So we already know the answer to this. This answer is 840, okay? What about the probability that x is less than or equal to 3? Here, I'll show you a trick here. You can just like grab this. You don't have to go into that screen we were in before. You can just substitute the number 1 for 3, and it'll give you the answer for that. So the probability that x is going to be less than or equal to 3 is a very big number. It's 0.9996, okay? All right, moving on. Number 7. The local bus service does not have a good reputation. The 8 a.m. bus will run late on average 2 days out of every 5. For any week of the year taken at random, find the probability of the 8 a.m. bus being on time. They actually give us the probability of the bus being late as 2/5, which is also known as 0.4, right? But the probability that they're asking for is the probability of the bus being on time. So we're going to define success as the probability of being on time on 1 day, and then we're going to say that that is going to be 3/5, which is also equal to 0.6, okay? So we're going to use probability equals 0.6 for all of these. Now, on these examples, what's varying is number of trials and number of successes. So, like for the first one, it says what's the probability that the bus is on time for 7 days in the week. And so that would be n equals 7. We want the probability that x is equal to 7 for the whole week, right? And then the probability is 0.6. Okay, and so in the calculator, we're going to use the x value of 7, and we're also going to use, are we going to use PDF or CDF? In this case, we're going to use CDF because the only way we're going to have success is if we do all 7 days, right? Okay, next one. So only on Monday. So again, we're going to, well, what's the probability of the bus being on time only on Monday? That means that we only have one trial, right? We have one trial, and, oh, I see, only on Monday. So only on Monday, and then all the other days it's late, right? So that means that it would be late, and then on time, and then late, and then late, and then late, and late, etc., all the way to the end. So this is a very special one. It's not, you don't really need the binomial probability distribution to solve this. You could just put, oh, this is equal to 0 point on time, or late on Sunday, so it would be 0.4, and then you multiply it times 0.6 for Monday, and then you multiply it times 0.4 for Tuesday, Wednesday, Thursday, Friday, Saturday. So that would be 5 days. So for this one, you would do to the 5th. Okay? So it would be actually 0.4 to the 6th times 0.6. Okay. All right, next one for C. What is the probability of the bus being on time on any 6 days? So here we can use the binomial PDF, and we'll see why. So we're going to have n trials, and we want the probability that we get 6 successes, exactly 6 successes, because we want 6 days on time. Okay, and then the probability, of course, is 0.6, p, and then we're going to use x equals 6, and we're going to use PDF because we want exactly 6, right? And last of all, for D, on time at least 4 days. So that would be n equals 7. Probability that x is greater than or equal to 4, because we want at least 4 days. So the probability is going to be 0.6. Now, what x do we use for this? Now, in this case, we actually are going to calculate. We're going to figure it out by doing 1 minus the probability that x is less than or equal to 3. And so we're going to use x equals 3, and we're going to use the CDF. And then we're going to subtract it from 1 later. Okay, now I'm going to go back and show you how to do these with the calculator. I just noticed that for this one here, we should do PDF and not CDF. I had written CDF, but now I put PDF. Okay? So let's do second distribution, go to the second page, and first we're going to put PDF because the first one is Binomial Pdf. 7 trials, P is 0.6, 7, 0.6, X value is going to be 7, and the value is 0.0280, 0.0280. The next one is not really a binomial CDF problem. You could do it with binomial CDF, but you could just multiply it out because it's just this. 0.4 to the 6, because it's 6 days of the week, you are late, and 0.6 time to the first power because 1 day you are on time. So that would be 0.00246. 0.00246. Let's do the next one. The next one is binary PDF. Actually, yeah, it'd be binary PDF. So we can go ahead and grab this one because it's pretty much the same. And we're going to put, instead of all 7 days, we're going to put any 6 days. So the answer is 0.131. And then the next one says on at least 4 days. So this would be using binary CDF. So let's do second distribution, go to the second page, go to CDF. We're going to put 7 trials, 0.6 is the probability will be on time, and the X value is going to be, let's see, 3, because we want 3 or less. And remember, we're figuring out the inverse probability here, so we're going to have to subtract this from 1, because we can only figure out, the calculator only figures out the probability of something or less. It can't figure out the probability of something or more. So it's going to be 0.710. 0.710. Okay. Number 9. During a season, a basketball player has a 94% success rate in shooting from the free throw line. In one match, the basketballer has 20 shots from the free throw line. Find the probability that the basketballer is successful on all 20 throws and at least 18 throws. And find the expected number of successful throws for the match. Okay, so the probability that he's going to be successful in all 20 throws, all shots. Okay, binomial. We'll go to Binomial Pdf, because in this case it's PDF. We're looking for the probability that x is equal to 20, so it would be PDF, not CDF, right? And we're going to put 20 shots, and we're going to put the probability he has a success is 0.94, which is really good. And we're going to put that he gets 20 successes, and it gives us a probability of 0.290. Okay, and then it says at least 18 throws. At least 18 throws, that's kind of a complicated one, because actually that's the probability that x is less than or equal, or I'm sorry, that it's greater than or equal to 18, which is actually 1 minus the probability that it is less than or equal to 17. So this the calculator can't do. This the calculator cannot do. So let's do the probability that it's less than 17. So we go to the second page, we do Binomial Cdf, we say there's 20 trials, the p is 0.94, the x is going to be 17, because you can always figure out 0 to 17, you can't figure out 18 to 20. And we figure out the probability is going to be 0.115 of this, but then we have to subtract it from 1 minus, and then it gives us 0.885. 0.885. So the probability that he gets, he makes at least 18 is actually quite a bit higher than the probability that he makes 20. Find the expected number of successful throws for the match. So the expected number would be the number of shots taken times the number of the probability of success. That's a pretty easy calculation, right? So 20 times 0.94 is going to give us the expected number, which is 18.8. And this video is getting too long, so I'm going to continue the remaining problems on the next video.